All right, just some notation as we get into chapter 10. You'll get good at writing sigma, the Greek sigma, because we're going to be using that frequently. Right? Without sigma, this notation is the notation for what? Do you know what that means? Not a series. A series is when this is a sequence. Very good. All right, a sequence. A sequence is simply a list. The list is separated by commas, so A1, comma, A2, comma, A3, comma, dot, 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 A sub n is the end. Okay, so a sequence is simply a list. That is the difference. Now, some of you are also using the other S word. Okay, when you throw sigma in front of that, all right, that becomes what's called a series. A series is a sum. And so the difference is now you're in A1 plus A2 plus A3 plus dot, 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 plus to the end. So it's a total. So sequences, series, two letters that start with S. Another way you can think of it is two letters that start with T. These are terms. This is a total. Okay? So just so you understand the notation that we're talking about of which is which. We talked about the convergence of both. Does a sequence converge? That means do its terms converge to a single number where every term would be converging to that value. That's like an asymptote. We talk about will a series converge? Okay, that's will this converge the total to a particular total number of when you add them all up. All right, so for each example, we're going to talk about the convergence of both for now. So here's our first example. All right, determine the convergence versus the divergence. So it's one or the other. Of the series -1 to the n as n goes from 1 to infinity. And we're going to do this right now by exploration. So, Megan, that's kind of like what you were doing on your test. Right? You're just trying it. And that at least gets you some points, and it at least tells you, especially on the multiple choice, you can figure it out. Okay, so we want to make a little table, I think, to organize ourselves. And our table is going to have 3 rows to it. We'll have an n row. We'll have an A sub n row, and we'll have a sigma A sub n row. So we're just going to explore. I think the first 6 terms should do it. So 1, 2, 3, 4, 5, and 6. All right, what is the value of the sequence for 1, 2, 3, 4, 5, 6? What's the term 1? Okay, the term 1 is negative 1. What is the term 2? 1. Negative, and then negative 1, 1, negative 1, and 1. So we say the sequence, which is just a list of terms, diverges. Okay, I told you the name of this. This is called the alternating sequence. It will always diverge. You'll be able to use that in lots of other, to get you out of lots of other messes. Alternating. All right, let's look at the sum. Well, for the first term, the sum is how much? Negative 1. For the second term, the sum is 0. The third term, the third part, we call these partial sums. So the first partial sum was negative 1. The second partial sum is terms 1 and 2 added together. That was 0. What's the third partial sum? Back to 1. What's the fourth partial sum? Okay, fifth, negative 1, sixth, 0. This also diverges with an alternating nature. So this is kind of the famous sequence and series called the alternating sequence and series. It will always be divergent in both its sequence and its series. Its terms diverge, its total diverges. Okay, so we just did that by exploration. Okay, good? All right, so let's try a different one. And we'll do another one by exploration before we come up with the test that we can use. So, explore the convergence or divergence of the series from 1 to infinity of 3 over 10 to the n. So I think 6 is going to be good for this too. All right, n, the sequence a sub n, and the series. And we'll do 1, 2, 3, 4, 5. Oops, didn't make it long enough. 6. Okay, let's do our first 6 terms of the sequence. All right, first term is 0.3. That's 3 over 10. Second term, 0.03. That's 3 over 100. Okay. Then we have 0.003. 0.0003. All right, 1, 2, 3, 4, 5, 6. Okay, what would you say is happening as we explore those terms? They are converging. They're getting smaller and smaller and smaller as they approach. No, as n approaches infinity, the sequence approaches 0. So this converges to 0. Will it ever get to 0? No. Okay, but it does converge as a sequence. The terms converge to 0. That doesn't mean the total is going to converge to 0. but the terms converge to 0. Okay, let's start investigating the partial sums. Okay, what's the first partial sum? Okay, what is the second partial sum? 0.33. The next. Okay. All right, so our partial sums definitely have a pattern to them. We also feel like they are converging, but what is the total converging to? 0.3 bar, which is 1/3, exactly. And so the total also converges to 1/3. So your terms can converge to one value where your total converges to something else. Okay, this is an example of a geometric series, because the geometric series is always produced by multiplication. So each term in the term list of the sequence, what is it being multiplied by? 0.1, and then multiplied again by 0.1, and then multiplied again by 0.1, 1/10. Oops. 3/10 to the n is a geometric series, or geometric sequence, with r being equal to 0.1. R is what is constantly being multiplied from one term to the next. Okay, this leads us to our very first test for convergence. So you probably should put it in your notes, but then you'll probably want to make a flashcard for it for easy reference also. Okay? All right, so this is the geometric series test. And it says the following. If A sub n is geometric with a specific r that is between 0 and 1. Actually, we can do it for negatives. We'll just combine it. I was going to do two separate cases, but we can combine it. It's fine. Right, it cannot be 1. It has to be less than. If it's equal to 1, then that's a whole different thing. Okay. All right, if it's a geometric series with r between those two, then this series will always converge. And, more specifically, it converges to a specific total. Okay? We write the total that way. That means we're showing the sum of infinitely many terms. It's not a partial sum. A partial sum would be like s sub 3. That would be the sum of the first 3 terms, or s sub 10. This is a complete sum. S sub infinity is the first term over 1 minus r. And that's your first test of chapter 10. Okay, I'm going to pause. Okay, our next 3 examples. Sometimes it is easy to spot a geometric series. It's like you look at it, oh yeah, I can easily tell what the multiplier is. Boom, 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 boom. Other times, it's not as obvious that it's going to be geometric until you kind of plug and chug a little bit and take a look at the first couple terms, and then you realize, oh, this is geometric after all. So let me do a couple of each with you. All right, so first question. Will the series from 0 to infinity of 2 to the 3/5 to the n converge? As long as you distribute it back in, once you've kind of, yeah. All that matters is the multiplier. Okay, so if I'm just sort of exploring this a little bit, my terms are going to be, what's the first one? If I drop 0 in, what do I get? I get 2. My second one will be 2 times 3/5. I don't need to work it out. My next one would be 2 times 3/5 squared. 2 times 3/5 cubed, etc. Is this or is this not geometric? It is geometric. What's the r? Right, the thing that's changing, the thing that's multiplying every time. And so this is geometric with r being equal to 3/5. And so according to the test, this should converge, this will converge, because the r value is between -1 and +1. And so this will converge to an infinite sum of, okay, and then we need the first term, which we determined to be 2, over 1 minus the multiplier 3/5. So that's 2 over 2/5, which is what? Yes. And so this series will converge to a sum total of 5.
When you write the term or sequence, you have to change up the
Not from me.
Okay.
All right, next one. Okay, will the following pi halves plus pi squared fourths plus pi cubed eighths plus pi fourth sixteenths plus ... bracket converge? So this time you were given it as a series already written out as a infinite sum. And so do you recognize whether this is or isn't geometric? Okay? Is there a constant multiplier that goes, so this is geometric with r being equal to the numerator multiplied by pi and the bottom being multiplied by 2. Okay, so will it converge or diverge?
Diverge.
What's the value of pi over 2? 3.14159 divided by 2, which is, this is greater than 1. So it's not going to converge. Will not converge. Done.
So this rule is also the reverse one, so
if it's not equal to 1. Okay, equal to 1 is a whole separate case. So if it's if it's greater than 1 or less than -1, but the equal to 1 or -1, that's going to be a separate case. Okay. All right. right, this is the last one I have for us. All right, will the series starting at 1 ending at the infinite term of cosine n, okay, so 2 to the n, of pi n, or n pi, let's do n pi, that's better, n pi minus pi fourths. Converge.
Why would you do this?
It's cool. All right, we are going to have to explore this one a little bit. Can you factor out pi? No. No, you don't want to do that. No. Okay, so I think it might help, at least it helps me. I need to write this out. I just need to see what the terms are going to be. All right. When n is 1, I will be dealing with cosine to the first of pi minus pi fourths. I'll figure that out later. Okay, when n is 2, what will I be dealing with? Cosine squared of 2 pi minus pi fourths. When n is 3, cosine cubed of 3 pi minus pi fourths. I think 4 might be enough. We might get it by 4. Okay, 4 cosine to the fourth of 4 pi minus pi fourths. It helped me when I was thinking about this question to think about what quadrant I was in. Okay, pi minus pi fourths on a unit circle is quadrant 2. 2 pi minus pi fourths was quadrant 4. 3 pi put me back in quadrant 2. 4 pi put me back in quadrant 4. Just helped me think about that. Okay. All right, what is the cosine when you're in quadrant 2 at basically 3 pi fourths? Negative what? Negative rad 2 over 2. All right. What is the cosine when you're in quadrant 4 at 7 pi fourths? Positive rad 2 over 2, but then what do I have to do to that? I have to square it. Okay. What's the quadrant when I'm back in quadrant 2 again? Negative rad 2 over 2, but what do I have to do to it? Cube it. And when I'm back in quadrant 4 again, I'm back to positive rad 2 over 2, but I have to fourth it. Okay, so what is it getting multiplied by every single time? Okay, so this is indeed geometric. And its multiplier is negative rad 2 over 2. Now, does that fall within the range of what we need? Okay, that's between 1 and negative 1. Yay. Okay, so it means it's going to converge. And it's going to converge to the specific infinite sum of, all right, we need the first term, which was what? Negative rad 2 over 2, over 1 minus the multiplier, which was also negative rad 2 over 2. So I have negative rad 2 over 2 over 1 plus rad 2 over 2. Multiply everything by 2 to get rid of the fractions. So you have negative rad 2 over 2 plus rad 2 would probably be the simplest way to write that. You just multiply everything by the 2, and that's what the series will sum to and converge to that total.